Welcome to the second video in a series of videos looking at graph theory, specifically using the software Graphstation. I'm going to start with an image, and I actually took this image from Google, and it is a place called Kaliningrad in Russia, and it was taken at the time of the 2018 World Cup, and you can see that the fan central is here. This is the Kaliningrad Stadium. And nearby there is a river called the Pregolya River. No doubt Russians will pronounce that differently. Apologies for that, but it is of significant importance, this intersection here, because this is where graph theory, many believe, started. And I'm going to paste in another image now, because back in the 18th century, it was actually called Konigsberg. So if I just paste this in now, and this is what it looked like. And I've got a picture of Leonhard Euler here, and I'm going to talk about where he comes into the picture very soon. But at the time, there were 7 bridges that crossed over the rivers, or the river, and people who lived in the nearby town wondered whether or not it was possible to actually take a walk from any point and travel over all 7 bridges without actually crossing the same bridge twice. I can't in this case, as you can see, I can't get to this bridge. If I start from, say, here, I can go through, and again I can't. Obviously I'm not drawn on screen, so it does make it a little bit more difficult. Now, what Euler did was he looked at the problem and he tried to represent it in terms of the land masses and the relationship between those. So what I'm going to do, I'm going to clear graph, start a new one, and I'll talk about exactly what it did. Now in my image library here, I've got bridges 1, and what I'm going to do, I'm going to add some nodes in here. I put 4 nodes in. Each node represents a land mass outside of the water, and I'm going to use the curve here to try and draw in the bridges. Now, it's really important that you click on hide edge and hide detail and smart edge before you do this, otherwise the graphs look a little bit messy. Now I select the curve. It doesn't matter where you start from each time, but I'm literally going to draw in all 7 bridges. And that diagram represents the 7 bridges of Konigsberg. We've got 4 nodes, and we've got connections which represent the bridges here. You can see there's 1, 2, 3, 4, 5, 6. Oh, I haven't put a 7th one in. 7. Now what we're going to do, we're going to try and make that journey using the manual tracer. So that's up here. I'm going to just bring it down, and what you should be able to see, it doesn't matter where we start because we don't know if it's possible or not. The people wondered, did they find out? So I'm going to start from C, go to B, D, A. As you can see, in that instance, it wasn't possible. You may want to pause the video at this point if you're running a lesson and you want your students to have a go for themselves. What I'm going to do, I'm going to try 1 or 2 other ways to do it. You can see very quickly I'm having difficulty. So what did Euler do, and how did he solve the problem? Well, what Euler did was he thought about it, and he thought, well, if you travel over a bridge, then you need to come back, which makes sense, unless it was your final destination, or it was the place you started from. So he said, if there was a possible solution, and if there was going to be an odd number of edges, then it must be exactly 2. If they were all even, that was fine, that worked. But if it was going to be odd, they had to be exactly 2. Now, if we count the odd edges up here, we've got 3, we've got 3, we've got 3, and we've got 5. By the way, the term here is degree. So node A has got degree 5, node C has got degree 3, B degree 3, and D degree 3. So all 4 have got an odd number of edges. So Euler said it can't be done, and it can't be. No matter how long you try, you cannot do it. So let's change the rules a little bit, and we're going to add in another edge. So we've now got 8 bridges. We've built another bridge. Now what have we got now? Let's look at it. We've got 4, 3, 6, and 3. So we've got node C and node D have both got an odd number of edges. Now, providing I start from that point, either of those nodes, I can do it in theory. Let's give it a try. C to A, back to C, B, A, B, D, A, and back to D. Success. Now, Euler himself didn't actually use the terms node, vertices, edge, etc. Those came more than a century later, but the solution was significant, and in that it was the start of graph theory. So what I'm going to do, I'm going to sort of clear that graph. I'm going to get a bit more complicated, and I'm going to use bridges 2. I could add these manually, but I've actually already got a template built there, and I've got one somewhere down here, then no bridges. Now when this graph appears, as you can see, there's lots of sort of weight and direction on. That's what the graphs look like as you draw them, unless you actually check these two, and it will take a lot of the work away, a lot of the complexity away from viewing the graph. Now what we've got here, we've got 10 nodes, and we've got how many edges? Well, if you look at the detail, okay, 17 edges, 10 nodes. By the way, in the earlier video, it was showing more nodes than it should have. That's because it was factoring in the ones I'd deleted. So I have fixed that, so apologize if you've just watched that and noticed it. So what I'm going to do, I'm going to show you at this point another one of the features, which is the panels. Now there's quite a few panels on here. Some of these are on the Pro version, but I'm just going to use the Eulerian one because I'm interested to find out how many of the nodes have got an odd number of degrees. And there's a little test on here. If I just click there, and we can see that C and G have got an odd number of connections or odd number of edges. So this graph can be solved. There is an Eulerian path around it. In other words, when I say Eulerian path, I can start at one node and I can visit every edge in the graph once and finish at the other. So let's try that. So I don't need this on. I'm going to use the manual one anyway. So start at C. By the way, I have a little trick which I use, which seems to work. If I travel over a bridge, I always try and travel back rather than move on if it's possible. And as I'm visiting these, you can see that it is going to be possible. Notice where I'm finishing. I started off on C and I'm finishing on G. So it can be done. Now, if I'd started somewhere else other than these two, it would not have been possible. Now, you may want to try that out with students if you're a teacher, obviously if they haven't seen this part of the video, and let them try to problem solve, let them try to work it out, and hopefully maybe if they've seen the earlier video they will be able to apply the theory and demonstrate how a more complex graph can be solved. What I'm going to do now, I've got some other built-in ones. I'm going to show you a one with an even number, which I think is this one. So this is another graph, and this one here has all got an even number of degrees. So if I'll just do a little test there, and it can be solved. There is a path. In actual fact, it's a circuit. So I should be able to start and end at the same point. Doesn't matter where I choose. Need to fix that message box. So if I go from here, and there you are, straightforward. I'll clear that again. Try from somewhere else. F. And back to F. So that has an Eulerian circuit. So what are some real world applications of this? Well, one of the things you might want to think about is if these are streets and you are, for example, collecting litter, or you could be a bin man, you know, collecting rubbish, or a postman delivering mail, and you need to visit each street, and you've got to visit various houses along the street. You don't want to be coming back along the same street twice. You want an efficient route. So that's a simpler application of it. Somewhere where you can visit each edge only once, do what you need to do, and then return either to the same point or stop at another point. And I think that pretty much concludes the second video. I hope you found it useful. Thank you.